What you are watching right now is footage of the Courier 1B satellite being launched on October 4th, 1960. This video has nothing to do with Courier 1B, but this was the only footage of a Thor Able-Star launch that I could find that hopefully won't result in a copyright strike. That is because 4 years later, on December 13th, 1964, a Thor Able-Star rocket just like this launched the actual satellite of interest for today, Transit 5B-5. Chances are you've already heard about this satellite. Even here on YouTube, you will find many videos showcasing the reception and sound of the signal that this satellite has been broadcasting, potentially for the last 60 years. It is a surviving relic of the age of the Cold War and the space race. The very same spacecraft, built in the US by the APL during the Lyndon B. Johnson administration, launched just 7 years after Sputnik 1 and 5 years before the first crewed moon landing, can still be heard going strong at the time of me publishing this video at the very end of 2024. There are even older defunct artificial satellites and dead rocket bodies in Earth orbit, but as far as we know, this is the oldest satellite still actively broadcasting a signal. In 1978, 14 years after the launch of Transit 5B-5, the Space Department of the APL published a document summarizing their accomplishments in the field of artificial satellites, fittingly titled Artificial Earth Satellites, designed and fabricated by the Johns Hopkins University Applied Physics Laboratory. This document goes into technical details and missions of every satellite the APL built or was involved in up to that point, except one. Indeed, there appear to be no mentions of Transit 5B-5 in any of the contemporary documents or literature, and it is my goal for this video to explain this discrepancy, which, upon closer inspection, appears to go far deeper than a simple typo. Let's start by talking about what the Transit satellite system was, as that will help us understand how Transit 5B-5 fits in. You may already know that Transit, also referred to as the NNSS or Navy Navigation Satellite System, acted as an early predecessor of today's GNSS or Global Navigation Satellite System that GPS satellites are a part of, together with their international equivalents. But not all Transit satellites fulfill this role. The initial 4 series of satellites, Transit 1, 2, 3 and 4, acted as prototypes and demonstrated the feasibility of the concept. They carried early versions of the instruments needed to perform their navigation role, as well as systems for power generation, attitude control, data storage and retransmission, and stabilization while in orbit. The Transit 5A series was the first with the specific goal of providing useful navigation services for the Navy. Of the 3 satellites launched between 1962 and 1963, only the last, Transit 5A3, managed to do so, as 5A1 suffered an in-orbit malfunction while 5A2 never even made it to orbit to begin with. Following the 5A series would be 2 successive ones, Transit 5BN and Transit 5E, launched together in 3 pairs of one 5BN and one 5E satellite each. The 5BN satellites would further develop the overall navigation mission of the system, also notably including alternative nuclear power sources in the form of RTGs that were present on the previous Transit 4 as well. The 5E series deviated from their navigational role, instead being more similar to the earlier experimental satellites. 5 of them were planned, from 5E1 to 5E5. The first 3 were launched together with the 5BN satellites as mentioned. The 4th, Transit 5E4, would never make it into production, while the last, Transit 5E5, was launched together with a member of a later series known as Transit Oscar. Between the end of the 5BN series and the start of the Oscar series, a single Transit 5C satellite was also launched, serving as the last prototype to finalize the design of the subsequent fully operational spacecraft for navigation. The Transit Oscar series would go on to become what made up the bulk of the NNSS navigation system, with Oscar being the phonetic alphabet term for the letter O, signifying its operational role. Of the 32 Transit Oscar satellites built, 24 were launched into space, with the remaining 8 staying on the ground. These were usually spares that ended up not being needed due to the Oscar satellites greatly exceeding their design lifetimes, especially the later ones. Of the 8 that stayed behind, 4 were rebuilt, renamed and launched to serve a different purpose. 1 was murdered by NASA as part of a ground-based experiment, and unfortunately I was not able to confirm the fate of the 3 remaining ground spares. Transit Oscar satellites were launched between 1964 and 1988, serving their operational role until 1996, at which point the much more capable GPS system was already up and running. Because the transit navigation system was based on the frequency shift of radio signals caused by the Doppler effect, each satellite had a pair of stable radio beacons, one containing telemetry and the other broadcasting stored messages, such as the individual satellite's orbital information needed for the subsequent position calculation. This pair of stable and coherent beacons made the satellite uniquely qualified to take on a new role of ionospheric research after the retirement of their navigational duties. By 1997 there were still at least 6 Oscars operational. I was able to find references to some still being used for science through 2003, and at least 2 Oscar 23 and 25 were still transmitting their 150 MHz beacon in 2010. At this point you're probably seeing how Transit 5B-5 does not fit into any of the series we just went through. The closest we got in terms of naming were the Transit 5BN satellites, however only 3 of those were built. To eliminate any possible naming confusion, we can look at the international designator which is assigned to each satellite. This is something you would have probably seen if you used any sort of tracking app, and in case of Transit 5B5 it is 1964-083 Delta. 1964 of course signifies the year during which the launch occurred. 083 means that this was the 83rd known successful orbital launch that year, and Delta, or the letter D, designates the individual object released by that launch. Because D is the 4th letter in the alphabet, we can assume that at least 3 other objects associated with the same launch were catalogued, and indeed if we look up 1964-083 on a site like spacetrack.org, we see that the list doesn't stop at D, but contains 19 different objects, going all the way to 1964-083 uniform. This is nothing unusual, as the vast majority of these are pieces of debris produced during the various stages of the orbital insertion, most of which have already decayed. There are however 2 objects classified as the main payload, Transit 5B-5 itself, and its companion, Transit 5E-5. This already sheds some light on Transit 5B-5's place in the system. Referring back to the original APL document, we see that this launch, which happened on December 13, 1964, carried Transit 5E-5 as well as Transit Oscar 2, revealing that at some point in time the name Transit 5B-5 was retroactively and possibly mistakenly assigned to Oscar 2. I decided to take a closer look at this elusive Transit 5B series, hoping to uncover the reasoning behind this name change. Today there are 7 of these satellites recognized as 5B. The first 3, Transit 5B1, 5B2 and 5B3, are the same satellites that were originally identified as Transit 5BN1, 5BN2 and 5BN3. This on its own would be an understandable change, perhaps a simple shortening of the series name from 5BN to 5B. Things however get weird once you look up Transit 5B4, which today is assigned to 1964-083 Bravo, a satellite that was originally named Transit Oscar 1. Going further, as we already discussed, Transit 5B5 is what was supposed to be Transit Oscar 2, but it takes a turn again when we arrive at Transit 5B6, which is now assigned to Transit Oscar 4, and 5B7 now being Oscar 5. This naming would imply that the 3 Transit 5BN satellites had something in common with the initial Oscar satellites, with the exception of Oscar 3, which for some reason was skipped and did not receive this treatment. One may think that this was because Oscar 3 never reached orbit, thus being excluded from the retroactive Transit 5B group. However, the same also happened to Transit 5BN3, but it was not skipped. No matter how much I think about this, I cannot see any possible connection that would warrant grouping these seemingly unrelated satellites into their own 5B series. There are big differences between the 5BN and Oscar satellites. If anything, the sole Transit 5C1 satellite has a lot more common with the Oscars than the 5BN satellites did. This strange name change also seems to have introduced a lot of confusion. Whenever we look up information about Transit 5B5, which we now know should rather be known as Transit Oscar 2, it is not uncommon to learn that it carried a nuclear power source. This appears to simply not be true, and was likely a mistake made because of this superficial association with the nuclear-carrying 5BN satellites. After the 5BN series, it was decided that future operational transit satellites would not carry this payload due to cost, regulatory and redundancy reasons. But, unfortunately for my own reading voice, the mystery of the Transit 5B5 satellite is still far from over. That is because, even if we do make the assumption that Transit 5B5 is Transit Oscar 2, some things still do not add up. Let's start by looking at the frequency that a satellite transmits at, 136.65 MHz. In many cases, signals from exceptionally old satellites only contain an unmodulated carrier wave, but even at first glance it is obvious that the signal coming from this particular satellite is being modulated with data. A simple way to try to figure out what kind of data this is would be looking into the APL document, as it contains the telecommunications details for every spacecraft mentioned. Using our newfound knowledge of Transit 5B-5 being Transit Oscar 2, we can read all about the radio configuration of the Transit operational series. Each satellite would transmit radio beacons at two different frequencies, 150 and 400 MHz. Both of these transmitters would share a common oscillator, ensuring that they stay in phase with each other. Carriers of these radio beacons could then have data modulated onto them. The 400 MHz modulator was connected to the output of the satellite's digital memory, where the data relevant to its mission would be stored, primarily orbital position and navigation messages. The modulator input of the 150 MHz transmitter was instead equipped with a switch, giving it the option of selecting from two data inputs. It could either be modulated by the same stored mission data as the 400 MHz transmitter, or by the satellite's own telemetry. Notably, there is a lack of any 136 MHz transmitter associated with the operational transit satellites used for navigation. It is possible that Oscar 2 carried an undocumented payload, but I believe this not to be likely because a later satellite, Oscar 14, did have a 136 MHz transmitter, and it is mentioned. But you know what satellite is confirmed to have a 136 MHz transmitter? Transit 5E5 was launched into the same orbit and on top of the same rocket as Transit Oscar 2. Unlike its navigation companion, 5E5's mission was to demonstrate and test new technologies while also gathering some scientific data. As mentioned during the introduction, it was the last of the 5E series, fifth one to be conceptualized, fourth to be constructed, and third to reach orbit, as 5E4 never made it into production and 5E2 was lost in a launch failure. Despite sharing the family name and being launched together, the physical designs of Transit 5E5 and Transit Oscar 2 differed substantially. To achieve enough power generation and attitude stabilization for its mission, Oscar 2 was equipped with four 1.7 meter long solar panels and an impressive 23 meter long gravity gradient stabilization boom, which would allow the satellite to maintain a stable Earth-facing orientation. The average weight of a Transit Oscar satellite is specified to have been around 50 kilograms, so quite light considering the large size the satellite would unfold into. On the other hand, we have Transit 5E5. Modest in comparison, it only had four small solar boxes attached to its cylindrical body for power generation. Though lacking the same massive gravity boom that Oscar 2 would have had, 5E5 was equipped with a comparably much smaller 4.8 meter long rod tipped with a magnetometer that would extend from the satellite, making sure its own magnetic fields do not disturb its readings. Overall, the much smaller Transit 5E5 is quoted to weigh 77.4 kilograms, about 65% more than the larger Oscar 2 would. But, and perhaps more importantly for now, Transit 5E5 is specifically mentioned to have used the 136 MHz band for its telemetry downlink, with additional transmitters at 162 and 324 MHz, which would have likely only consisted of an unmodulated carrier wave used for more precise orbit determination from the ground. At this point in the video, you are probably starting to see what I am suggesting, so let's just talk about it directly. The possibility of Transit 5E5 and Transit Oscar 2 being switched in the catalog, meaning that what we know today as Transit 5B-5 is actually 5E5 and 5E5 is Oscar 2, came to my mind right after learning about the frequency information, so I started looking at other ways that could help us differentiate the two. The first was looking at the history of their orbits. Because both 5E5 and Oscar 2 were deployed into the exact same orbit, it should be possible to tell the two apart by looking at how their altitudes decayed over time. This is because a smaller, heavier and denser satellite like 5E5 encounters less residual atmospheric drag and conserves its momentum better than the larger and lighter Oscar 2. If we were to plot the average altitude of the two against time, we should see two curves starting in the same point, with one traced by Oscar 2 descending faster than 5E5's. So, let's do just that. As expected, we have a clear deviation of the two curves, with one decaying faster than the other. The apparent stair-step pattern in the plot is caused by heightened solar activity, which increases the density of the upper parts of the atmosphere that are still present at these altitudes, resulting in periods of increased drag and accelerated decay of satellites in Earth orbit. From what we know about these two satellites, the curve that is decaying faster should be transit Oscar 2, while the one that's better at retaining its altitude should be transit 5E5. And yet, after adding the labels, we see the exact opposite. The satellite that is currently labeled as transit 5B-5 and that should be transit Oscar 2 seems to be decaying slower than the one currently labeled as transit 5E5, something which does support the theory of the two satellites being mislabeled and swapped. Another clue for the satellite's identity would be the contents of the radio signal itself. As mentioned earlier, because this is an actual modulated signal transmitting data, we have the luxury of looking at its properties and structure, if any, and seeing how it could relate to other transit satellites. Let's first take a look at the signal's spectrum. At the center, we have the carrier. Roughly 5 kHz above and below is where some analog telemetry seems to be centered. This is actually the source of the sound now associated with transit 5B5 reception, but it actually is not where most of the data lies. We have to go further from the carrier to roughly 10 kHz above and below, where we see and hear the much higher rate, at least comparably, digital telemetry. The signals further away from the carrier simply appear to be higher order sidebands produced by these two data streams, and thus do not carry any unique information. A detailed analysis of these signals has been done by Mike Kenny from Melbourne, Australia, who published 2 documents with information that is invaluable for our task of finding out which satellite is which. In his first report from 2010, Mike looks at the overall properties of the signal, such as the data rates and modulations involved in the 2 telemetry subcarriers, while also comparing it to some other contemporary spacecraft. It is also in this document that Mike points out the strange naming inconsistency and considers the possibility of transit Oscar 2 and transit 5E5 being swapped, even though he adds that this swap was unlikely to have happened and theorizes that perhaps an extra telemetry transmitter was included on Oscar 2. When I first read this, I found it extremely validating. Mike's second report from 2019 and 2020 goes more into the details of the actual contents of the telemetry, trying to find patterns and reverse engineer it as much as possible despite the lack of documentation or information about what this signal is actually meant to be. This is because in both cases, whether the signal is coming from transit Oscar 2 or transit 5E5, there appears to be no official documentation about it. In the first case, there are simply no mentions of a 136 MHz telemetry transmitter on Oscar 2 whatsoever. Transit 5E5 is officially stated to have one, and while at some point in time a detailed description of its telemetry structure and format might have existed, it appears to not have been preserved via freely accessible online channels. Of the 3 Transit 5E satellites that made it into space, Transit 5E1 seems to have gotten the most attention, with one surviving online document in particular describing parts of its telemetry downlink system in detail. The same document was also quoted by Mike in his own investigation, all of which will be linked in the description. The best we can do is compare the properties of the signal observed today from what we call Transit 5B5 to what would be expected from Transit 5E1. Being 5B5's somewhat close relative. The signal we are seeing today is centered at 136.65 MHz. Transit 5E1 is quoted to have transmitted its telemetry at 136.65 MHz. We are observing 2 data subcarriers modulated onto the signal, an analog one with an offset of around 5 kHz and a digital one with an offset of 10.5 kHz. Transit 5E1 had 2 telemetry subcarriers, one with digital data at 10.5 kHz and one with analog data at 5.4 kHz. Next, we can compare the data rate of the digital telemetry, as that will be more reliable than looking at the analog one, which seems to have somewhat degraded by now, with occasional corrupted symbols being modulated far exceeding the intended original bandwidth. The 5E1 document specifies the digital rate to be 195.5 bits per second, and this is where we diverge. In Mike's observations, a bitrate of 389 was determined, which was confirmed in an investigation done by Xerbo in 2021, who later arrived at a much more specific value of 390.59375 by referencing another old document containing the exact nominal base clock frequency used in transit satellites. This data rate appears to be exactly twice as fast as what 5E1 would have had. Mike Kenny postulates that at some point during its long life, the satellite could have suffered a malfunction of a divider that is used to derive this rate from the onboard clock. Initially, I did not really think something like that was likely to happen, but after I compared modern recordings of this signal to audio snippets from 1973, preserved on the internet thanks to the admirable efforts of Matthias Bopp and his website, link in the description, it is apparent that indeed both the analog and digital telemetry are now being read out at twice the speed. While this is very interesting and would warrant looking into the signal structure further to see if maybe some meaningful data from the satellite sensors or instruments could be recovered, it does not really make a difference in our efforts to distinguish the satellites. Sped up or not, the radio signal, its frequency, modulation and contents appear to be more in line with a Transit 5E satellite rather than a Transit Oscar. When I look at all of this, I personally am inclined to believe that the satellite we are observing today, that we know as Transit 5B-5, is in fact Transit 5E5. The observed frequency of its radio signal, the modulation and subcarrier spacing it uses, its orbital decay profile, and the fact that while Transit Oscar 2 was officially declared dead, while there seems to have never been a confirmed mission end for Transit 5E5, all seem to point at what I think is the probable event of the two satellites' orbital elements being swapped, effectively resulting in their recognized identities being switched. I am releasing this video on the 60th anniversary of the Transit 5E5 and Transit Oscar 2 launch, and it is my hope that if indeed it is Transit 5E5 that has managed to stay partially operational for all of this time, dutifully transmitting its signal every time there was enough solar power to do so, that I have at least managed to give it some of the well-deserved credit. Perhaps more information about these two satellites will be revealed with time, or a better method of reliably distinguishing the two will be devised that ultimately proves that it was Oscar 2 all this time. While direct optical observation is unlikely, there is a massive sample size of defunct Transit Oscar satellites still in orbit that could be used for a comparison. But ultimately, the identity of these old satellites is of little to no concern to those in charge of cataloging them. With thousands, soon to be tens of thousands of satellites all operating in low Earth orbit simultaneously, all that matters is that they don't get in anyone's way, and as long as their orbits and positions are tracked, their labels don't matter. I wanted to end this video with footage of me receiving the satellite, however, due to the apparent long-term variation of its signal strength, combined with an unusual amount of RF interference present at the time, all I managed to get was the center carrier with very weak data sidebands drowning in noise, and capping off with that feels like it would just be disrespectful to both you and the satellite. Instead, what you've been watching in the background is a previous recording I made of the satellite signal with my Yagi antenna from my backyard. The iconic analog telemetry can be heard as the repeating sequence of variable tones, while the digital telemetry sounds like the higher frequency, rough noise. Today, this signal overlaps the upper edge of the airband, being a very mild, basically non-existent inconvenience for digital air traffic control, while serving as an interesting, easy-to-receive curiosity for radio amateurs and SDR satellite reception enthusiasts alike. Many decades ago, the same signal was crucial for fulfilling the mission of this satellite, furthering our scientific and engineering knowledge. There will be dedicated ground stations tracking this signal with high-gain antennas, decoding and storing the data on magnetic tapes for further processing. And while it is a widely known fact that back then things were built to last, and despite the visible deterioration of the data structure recovered from the signal, I'm going to assume that none of the people who worked on this spacecraft expected it to remain somewhat operational for this long.